All right, so this is section 2.5 of Math 146. Um, this is modeling with functions. Basically, this is going to be word problems. And I am not going to lie to you when I tell you that even when you can do this in calculus, because there will be some ways that you learn in calculus that are easier than this is still not the easiest of sections to do. And that's because they are word problems. So the biggest thing is you're going to have to decipher what's going on in the problem, with the verb, with the, the verbal aspect of it. And then you're also going to have to be able to do the math. And I will tell you that this is probably one of the more algebraically intensive sections. Some of the stuff won't be, but some of it will be. Um, it is going to rely on the fact that you understand in the beginning of this, the examples that we go through at least are going to start off with quadratics. So you're going to have to understand some basic properties of quadratics to do it. And then there's going to be some other things that we do that are going to be non-quadratic. There is no way I can cover all of the possible examples. So I'm going to do as many as I can, whether it's a 1 or 2 video lesson is going to depend on how long it takes me to get through each one of these. And I strongly suggest that when you go to the homework in MyMathLab, that if you get stuck on a problem and it's likely to happen at least once or twice, please do the view an example problem, or whatever the options are that state something like that there to help you out, because this is not going, like I said, this is not going to be the quickest and easiest section. With that said, let's go ahead and get started. We're going to jump right in with an example. And this one has to do with revenue. All right, and revenue is defined to be um, the price of something times how many units of that thing you sell. So it is the price times the number of units sold. So in our first example, we are going to be given um, that the price is going to be P. So we will define the price to be the variable P. And it's going to tell us that X is going to be 21,000 minus 150p, and X represents the number of, in this case, we're going to say calculators sold. So we're talking about the price of calculators and the number of calculators sold. So if I want to find an expression that represents the revenue, it's simply the price times the number of calculators sold. Well, if the price itself is P and the number of calculators sold is represented by 21,000 minus 150p, then your revenue, we'll call it, we'll just say revenue, R, is going to be the number of calculators sold times the price. And again, that should make sense. The revenue is kind of like how much money you're bringing in. So you're going to take however many things you're selling times however much it costs to sell them, and that's going to be your revenue. So there's an expression for the revenue. What's the domain of this? This is one where you kind of have to think about it, and there's some logic involved, and then there's going to be a little math involved. So we're talking about the domain, which is going to, in this case, go with your P value. P happens to be your independent variable, where R is the dependent variable because the revenue depends upon the price. So since we're talking about the number of units or calculators sold in this case, you can't sell less than 0. So 0 is the bottom of your domain. So we could sell 0, which would be bad for business. And then we could sell up to a certain amount based upon our information. So what you need to do is you need to figure out what the domain is based upon the revenue equation that we're given. Basically, the way you do it is you take each one of these things in the revenue and you set it equal to 0. So we set the revenue, equal to 0, and we'll solve it. Well, that's where we get the p equals 0, because if you take that, p would equal 0, or you would get that 21,000 minus 150p is equal to 0. That one we need to do a little solving. So add 150p to both sides, and then divide both sides by 150. And well, I can't do that one necessarily in my head, not easily anyway. Probably have to plug that thing into a calculator. I believe you come up with 140. And no, I did not do that in my head. I actually had it worked out. So that tells us the maximum for the p. So your domain is 0 to 140, okay, for your revenue. I'm sorry, for your price, p. So you can really only price these things from 0 to $140. Making a price less than 0 makes no sense. And you can only maximize the price at $140 in order to actually have a revenue. So what unit price should be used to maximize the revenue, to get the maximum amount of money? So think about it. If you price it at 0, you're not making anything. So that doesn't make any sense. If you price it at $140, it's probably priced too high, and you're not going to get the maximum amount of revenue. So here's how you find the maximum. The revenue function itself is a quadratic, which if we were to distribute the p, you would get that the revenue is 21,000p minus 150p squared. Okay, that's a quadratic because you have a squared term in there, and that's the highest one. So if you want to figure out the maximum, the easiest way to do that is this little equation, negative b over 2a. Excuse me, that expression, that's not actually an equation. But your maximum is going to be located when your independent variable, in this case it's p, sometimes it's x, sometimes it's t. It just depends on what the variable is they use. But that's going to be negative b over 2a. Now this comes from the whole setting this stuff up as a quadratic formula. So remember that the number out in front of the squared term, that's a. So that would be like a. And then the number out in front of the p term right there, that's b. So negative b, negative 21,000, over 2 times a, which is going to be 2 times negative 150. So we get negative 21,000 divided by negative 300. Of course, the negatives are going to cancel out. The zeros here are going to cancel out. So you get 210 divided by 3, which should be 70. So that is going to be a p-value. That will be the price, which is going to maximize the revenue. It just happens to be right in the middle of this thing. So the price of $70 will maximize the revenue. Well, that's nice to know what you would have to charge to maximize the revenue, but most people would probably like to know, what is that revenue? What am I going to make if I charge that much? Okay, and that'll be part D. That's the easier part, because you're just going to simply do R evaluated at 70. So we're going to plug 70 in, and it doesn't matter which R you go from. You could go from this one, or you could go from this one, whichever makes it easier to do. Doesn't really matter. With these numbers getting kind of large here, this would probably be something that would be on a calculator portion of a problem or a test or something like that. That's not something I expect most people to do without it. And you would actually get 735,000. $735,000. That would be the maximum revenue given the fact that we were to maximize the price at $70, or to get the maximum revenue, we would make the price $70 per unit. And then the last question it might say is, how many units are sold at that price? So let's write that part down. How many units sold at that price? Well, remember the number of units comes from this expression right here. That was basically the expression that they told us the number of units. So at the price of $70, we are simply going to plug that into the X thing, which was, scrolling back up, 21,000 minus 150p. 21,000 minus 150, and the price was $70. So you would go ahead and plug that stuff in there, and you would get that the number of units in this case, work this out to be 10,500 units sold. Or calculators. Sold. All right, not bad. So the biggest thing there is, again, understanding how the equations fit together, knowing this piece right here, because this is a quadratic, and because this piece right here was negative, which is the leading coefficient, that indicates that the quadratic opens down. So if we think of this graphically, I'm not going to actually sketch the correct graph, but if you were to take a graph of a quadratic which opens down, okay, you can tell by looking at that the maximum is going to occur at the vertex. Oops, that's supposed to be in red. Maximum is going to occur at the vertex. And technically, if you had a quadratic which opened up, the minimum would occur at the vertex. But that's always going to be the case with a quadratic based upon properties of quadratics. And the way you find that point, it is negative b over 2a. And then the y value there is just plug negative b over 2a into the function. So it's f of negative b over 2a. That's a b on top. Trying my best. So that's how you will always be able to find the vertex given the quadratic equation that you have there. All right, let's move on to another type of example. Example 2. All right, so in this time, we're going to be maximizing the area of something enclosed by a fence. So what it says is we have 2,000 yards of fencing. We want to use all of this to enclose a rectangular field. What are the dimensions of the rectangular field that will maximize the area or give us the most area? So what dimensions will maximize the area? All right, so in order to do this, first of all, it might be a really good idea just to create a little sketch. Just have a rectangular field, nothing fancy. And with a rectangular field, we should know a couple of things. We should know that it's got a width and a length, or a base and a height, or however you want to say this with the rectangle. Typically, because it's talking about a rectangular field, I personally use width and length. It does not matter. You can use other versions of that. And typically, I also make the width the shorter and the length the longer piece. Again, that doesn't really matter as long as you keep it straight, but it helps to be consistent. All right, we want to maximize the area of this field. Well, the area, of course, of a rectangle is the length times the width, one side times the other side, right? So the area of a field is the length times the width. And that's what we want to maximize. The biggest thing is what we need to do is we need to put all of this into terms of one letter, because right now you've got length and width, and those are both independent because both of those things determine the area. We want to put it into terms of one variable. Well, there's some other information in the problem. They tell us that we have 200 yards of, 2,000 yards of fencing to deal with. Well, if I have 2,000 yards of fencing, basically that tells me what I have to put on the outside here of this fence, or the perimeter. And hopefully we know that the perimeter of a rectangle is 2 widths plus 2 lengths. So 2 widths plus 2 lengths. And they tell us in this case that our perimeter is 2,000 because we're trying to use the whole amount of yards of fencing that they gave us. What that does is this gives us what's called a secondary equation. It gives me an equation that I can use right here to solve for either L or for W, and in this case it doesn't really matter, and then substitute it back into the area equation that we're trying to maximize, trying to get the maximum area from. So let's go ahead and use our perimeter equation. The first thing that I see is that we can divide 2 out of both sides, which is going to make that nice. So if you divide 2 out of both sides of the equation, that you get the width plus the length equals 1,000. And then literally I can solve for L or for W. Again, it does not make any difference. In this case, I'm just going to solve for the W. Again, it doesn't matter. So if we solve for W, we would subtract L on both sides, which will be 1,000 minus L. Actually make that look like an L, kind of look like an E. All right, so now what I have is I have this equation right here, which is W, which I can take and I can put it right in there for that W, and that's going to eliminate the W and just leave us with an L to deal with. So my equation now for the area is L times 1,000 minus L. That in itself is a quadratic. I know because if I distribute 1,000 L minus L squared, that's a quadratic. The coefficient in front of the L squared is negative, so this means that this is something which opens down. The quadratic will open down, which means that at its vertex, just like we showed in that previous graph, it will have a maximum. So this is a good thing because we want this to have a maximum value. All right, so again, how do we find that maximum value? The expression negative b over 2a will give us the location of the maximum, or in this case, it's actually going to give us the L value. So negative b, remember this is b, so that's going to be negative 1,000 over 2a. A itself is the coefficient out here, which is technically negative 1, so 2 times negative 1. So negative 1,000 divided by negative 2 is positive 500. And technically, again, that is the L value that will maximize this. And I believe the question is asking for the dimensions, which we can now find because I have an expression right here that we simplified. W plus L equals 1,000. Well, if L is 500, we get W plus 500 equals 1,000. Subtracting 500 on both sides, we get the width to also be 500. So our dimensions are the width and the length are both 500. So you would get a 500 by 500. Did I put units on here? Yards. Yards squared or square yards. Those would be your dimensions, 500 by 500. And typically, unless there's something else going on, and you'll probably figure this out as you do problems, um, the greatest area of a rectangle is always going to be a square. So that's just kind of something good to keep in the back of your head. Now, granted, if we had done something different and said, oh, we need to add another whole thing of fencing someplace in the middle of this thing, or, maybe you've only got 3 sides of the fence because it's bordering, a house or something, that changes things. So it's not always going to be that. But when it's just a standard rectangle, the maximum area will always be created by a square. Again, just something good to let you know. All right. I think we'll do one more example in this one, and then we'll probably come back with one more video because, again, these take some time. So let's do example 3. All right, and this one's going to be about projectile motion. So we'll just say that, I don't know, a rock is thrown from a cliff 500 feet above the water. A lot of times it's going to tell you it's done at an angle of 45 degrees because the angle actually does matter. Angle of 45 degrees typically maximizes the flight of the projectile. If it tells you something else with a different degree of launch angle, that's something we'll get into when we get into the trig stuff. So for right now, just assume it's at a 45-degree angle. Let's see. It is thrown at 400 feet per second. So you're not expected at this point to necessarily write this equation. Usually it's given to you, which is nice. Eventually, if you take some physics and stuff like that, you'll be able to write the equation, or even some higher order calculus classes, you'll be able to write the equation out. For now, I will tell you that the equation that represents this, so the height, h of x, is going to be given as negative 32x squared divided by 400 squared plus x plus 500. All right, and hopefully what you understand from this is that 500 comes from the initial height that this thing is thrown. X here represents the distance, the horizontal distance, I should say, because it's an x value, and technically h of x is like a y value, so that's how you get the height. So ultimately, if you think about it, and I'm just going to do a quick sketch because this isn't going to be real, we're going to say that we've got this, here's 500, you've got your cliff that you're standing on, and you're going to throw this rock, and it's going to go up like this, and eventually it's going to come down and hit the water. So again, it is a quadratic because you can tell that you've got a negative 32x squared over 400 squared. 400 squared, I don't know why I wrote it like that. I could have just written it as 16,000. But in any case, the coefficient of x squared is a negative value, so it's a parabola which opens down. And then in this case, you actually have an extra constant there of 500, which we'll have to deal with. All right, so the questions might ask, what is the maximum height of the projectile? So let's find the maximum height of this rock. Nothing changes. Still negative b over 2a is how you're going to find the location of it, and then you're going to plug that value in to actually find the height. So negative b, that b part is the coefficient in front of your x term, so that's negative 1, divided by 2a. Okay, so this is a little bit more challenging. It's 2 times, and technically a is the coefficient, all of this, I kind of went over the square there. So all of this is the coefficient of x squared. So we write negative 32 over 400 squared. Negative b over 2a. Okay, again, not something that I expect you to do in this case without the aid of a calculator, although technically you could probably work it out, but that's going to end up working out to be 2,500. That is not the maximum height, that's the location. So basically that's this thing over here. Oops, kind of missed. Maximum height should be right about there. So now you have to plug 2,500 back into your original equation to get the actual height up here. So you're going to do h of 2,500. So you got to plug that one back in. Once again, I do not expect in this case for you to be able to do that without a calculator. You plug that back into the height equation and you should get 1,750 feet. That is the maximum height. The second question, or the second part, might say, how far from the base of the cliff will the projectile strike the water? How far from the base of the cliff will the rock hit the water? And if we want the rock to hit the water, so we're talking about this distance out there, we want to know the x distance. We want to know how long this thing went from here to here before it hit the water. If you want it to hit the water, we know that the height is 0 because it hit the water. So you're going to set 0 for h of x equals negative 32x squared over 400 squared plus x plus 500. Okay, again, not going to be an easy one here to do. Let's see if we can simplify this just a little bit first. So let's see, 400 squared is going to be 16,000. So it'll be negative 32 over 16,000 x squared plus x plus 500. Oh boy. So 32 is going to go into 160. I do know that much. 32 goes into 160, should be 5 times. So that means that we're going to get negative 1 over 5,000. If I did that correctly, I believe I did. Something about that feels wrong. It's because it's not 16,000, it's 160,000. That's why that's off. Yeah, 400 times 400 should be 4 times 4, it's 16, but 4 zeros, not 3 zeros. Okay, this makes much more sense. Okay, 32 goes into 160,000, 5,000 times. I knew that the answer was supposed to, or the number was supposed to be 5,000, and the denominator just wasn't getting y. So basically, you'd have to try and solve this quadratic. If you're trying to do this without a calculator, good on you. This is going to be a mess. Technically, you could factor this, I guess, or you could try to factor it. or you could use the quadratic formula if that works, and it does. But if that's easy enough for you to do, go for it. Um, I'm going to tell you that one way or the other, you're going to get the answers of, you should get x equals negative 458 and x equals 5,458. That is solving the quadratic. The negative 458 makes no sense because that is literally back here. So, oops, sorry. That is literally back here somewhere when that thing would have hit. So that makes no sense because that's like throwing the rock down and backwards from a cliff. It just doesn't make any sense. So the value that we're actually going to get here of 5,458, that's that value right there. That's the distance. So that one, and that would have been in feet, is your distance. All right, that is plenty enough for this video. I will come back with a second video, and in the second video, we're going to do a lot more of just setting stuff up and not necessarily completing the problems because there's a few things I want you all to see.